We are privileged tonight to have a new speaker. This is David Dana-Bashian. Dana-Bashian. He's kind of getting his feet wet. He's new to the speaking circus. And a little information about him. He's had 30 years experience in aerospace and control systems as an algorithm developer. And he has a BS in math, a BS in chemistry, ACS certified, and an MS in math. That's a master's degree in math. So with that, please welcome David Dana-Bashian.
Thank you, Jim. Thank you all for coming, and tonight's talk is 16 Nearly Impossible Issues for Evolutionists to Answer. There were a number of things that I discovered in my last couple of years in schooling, and a number of these will come to the forefront. The main objective is to sketch the 16 issues, which are mostly scientific, and then to show how the evolutionists' responses actually fall short. They don't fall short of something like what Jim was referring to, but rather they just fall short of science itself, especially known scientific laws, things that everybody should have already encountered by the time they were in high school or in college. So with that, one of the things that I was treated to in that year that I referred to was that there are 4 philosophical schools of thought. I want you to keep them in mind. How do we determine or know that something is true? The first of these is the absolutist, which means that somebody told you that it's so. The second is the empirical, which means somebody tested it to find out that it's so. The third is the pragmatic, which means somebody discovered that it works. And the fourth is the existential, which is to say somebody discovered that something occurred. And the preferred choice for this talk is empiricism. You might have seen this cartoon years ago where Columbus had a dialogue that looked something like this. She's a round like the apple, she's a flat like the pancake, and so forth.
Round, flat, round, flat, round, flat, round. Columbo, the world she's flat. The world she's around. She's flat. Look, King, she's round like the apple. She's flat like the pancake. Posta fazool. She's round, she's firm, she's fully packed. She's round like my head. She's flat like your head.
Now, what I mean by showing you this is that there are various perceptions that we bring to the table. Sometimes they're well-founded, and sometimes they're not. And it's only by discovery, by empiricism, by testing, by observing, by correlating, by cross-correlating that we ever come to any conclusions regarding at least the things here on Earth as to whether they're more likely or less likely to be so. And empiricism, I call it the dispassionate interchange. Here we have the scientific method. We form a hypothesis, we gather data, we gather evidence, we gather supporting works to see whether or not that might be so. We test our model in theory versus things that are real or practical. That's where the pragmatic side comes in. We collect, we measure, we observe, we correlate, we cross-correlate, and always in the questioning eye of the skeptic. And we might have some skeptics here too, and I welcome your comments at due season. And we're also modifying our conclusions. We might repeat some of those same steps as we mentioned. We might revise our hypothesis or our theory. In empiricism, there's no such thing as 0% or 100%. It's somewhere just above 0% or somewhere just below 100%. It might be a high probability, it might be a low probability, it might be something in between, but it's always subject to change depending upon what we find from new information as it happens to come in. Now, you might recognize this quote also. This might have been something that Rudyard Kipling might have spoken, but actually it wasn't. This is the famous blind men on the elephant quote, where it ends with the lines, each was partly in the right, and then in red, and all were in the wrong. This is another matter of perception. We don't always have everything available to us. We might have our blinders on, one way or the other. We're all subject to having our blinders on. Here's a general principle I also want to lead in with. Verified scientific laws don't displace other verified scientific laws. It's not as if something comes along and displaces something else that's already well established. That's just generally not what happens. Or, as 3 skeptical scientists said to Stephen Wolfram on 1 February 2003, and I was there to see that, the new science better agree with the old kind of science. We're going to see that happen again and again here. Maybe around Christmas time, you'll see the Miracle on 34th Street. And in there are a number of interesting quips that might have some relevance here. One of them is, you've heard of the French or English nation. Well, this is the imagination.
Do you know what the imagination is?
Oh, sure. That's when you see things, but they're not really there.
Well, that can be caused by other things, too. No, to me, the imagination is a place all by itself, a separate country. Now, you've heard of the French nation, the British nation. Well, this is the imagination. It's a wonderful place.
That's sometimes what theories that are posed turn out to be in the end. Nothing more than imagination. We want to deal with things that come to grips with what things actually are, and not something that is henceforth in the future and believed to be true later on without any solid proof. Also, the same Santa Claus character who was responsible for the first quote also gave us the second. I modified one word. You might recognize that word in red, where when I modify it says, I have great respect for science and great contempt for amateurs who go about practicing it. Sometimes it said meddling amateurs. Another thing I'd like to lay on the table has to do with extrapolation. Mathematics sometimes has to deal with interpolation, which is trying to fit points between other points, and extrapolation, which is trying to extend what we believe a phenomenon is beyond the point that we have any data points. Extrapolation is much more likely to encourage mischief than interpolation, especially if you're going backward into the unobservable past. And that's what a lot of where the mischief comes from. We don't have any way of extracting from the past a repeatable, observable event. In the courtroom, this is called circumstantial evidence, last time I checked. Now, evolutionists don't confine themselves to merely biology. For if that were the case, then something else could enter the picture and upset the whole paradigm. So it stands to reason that evolutionists would also want to explore other avenues, and I've listed some of them here. They might want to go for chemical, stellar nucleosynthesis, or molecular, abiogenesis. Or they might want to go the cosmological route with stellar nurseries if they're really there, galaxy formation, and it also extends to even language and society besides the biological implications. So a complete paradigm would have us going from whatever the origin would be up until now and maybe beyond. That's fair enough. We'll see whether or not what they have to present agrees with what we also know from science. But I want to say that it's not merely a biological thing that I'm referring to. I'm referring to all categories wherever it touches. Also in review are the laws of thermodynamics, which, by the way, you can find in any standard physical chemistry textbook or physics book. Here is mine from that same year that I referred to earlier. The 4 laws are as follows. The first one is mass energy of the universe is constant. Or in darkly humorous form, you can't win, the best you can do is break even. The second is entropy, which is the measure of disorder, increases unabatedly. Or in darkly humorous form, you can only break even at absolute zero. Sir Arthur Eddington, as quoted in Chapter 8, Section 2 of Gordon Barrow's physical chemistry textbook from 1922, said that entropy is time zero, and it said it led to interesting philosophical speculations. I should say so. The third law speaks for itself. absolute zero is unattainable. In other words, you can't reach absolute zero. There's also a zeroth law that says you must play the game. And so the implication from thermodynamics is you must lose. Here then are the 16 issues. First one is, why does anything exist? I'm going to go over them briefly and then in more detail in a moment. The second is, did the universe always exist? Third is, did the universe cause itself to exist? Fourth is, how can the universe avoid heat death, as if that were possible? Fifth is, how can any material travel faster than the speed of light? And you didn't think that was possible? Sixth, what is the origin, transportation, and distribution of carbon? A hardly covered topic. 7, how do any stars exist? 8, how do moons form? Also not covered very well. 9, what is the ongoing source of long-term comets? 10, how do any elements heavier than iron exist? Also not very well covered. 11, how do peptide bonds exist? Bonds between amino acids. 12, how do proteins have only left-handed amino acids? Only one of these two. What turned non-life into life? Skeptics who saw my talk earlier, that was the favorite one, I suppose. 14, how does metamorphosis occur? As opposed to amphibian metamorphosis, I'm going to be covering an aspect of insect metamorphosis. 15, how do major morphological changes occur? That is, between fish to amphibians to reptiles to birds or to mammals rather. 16, what creates information from gibberish? Those are the 16. You could add, of course, hundreds more. In fact, there are hundreds more in this book. Well, this is my last remaining print of it. It's called Flaws in the Theory of Evolution by Evan Shute. It goes to 24 chapters worth of things. First topic, why does anything exist? Well, if nothing exists, we don't have any space, we don't have any material, we don't have people, no meaning, nothing. From nothing, nothing comes, is also said in philosophy classes. I would propose that topic number 1 in this book, Roget's Pocket Thesaurus, is where to start. Roget's Pocket Thesaurus is more than merely a treasury of synonyms and antonyms, because we can study the structure of the language just by looking at the structure of the topics that are covered in this book. And it would stand to reason also that if topic number 1 is existence, that the latter topics in the book might have to do with possible causes of existence. We not only have to ask the question, why does anything exist, but why this particular amount of material exists. It's been estimated that there are approximately 10 to the 80th atoms in the universe. Why not 10 to the 79th? Why not 10 to the 81st? Why this particular amount? And why this particular distribution of the material? It's not scattered all over the universe where it's not economically viable for anything. It's in clumps. Even on the Earth, we see the distribution of precious materials being only in scattered places. Otherwise, that's what we see. We see clumps of material. We don't see, in other words, ores. And I'd like to say also something about quantum fluctuations. There is this widely held popular belief that nothing can turn into everything. I'd like to dispel that right now. The idea is that nothing turns into a particle and an antiparticle, and the particle and the antiparticle can come back together again, and they can keep repeating the step, this inversion, one to the other and the other into the one. Is that what really happens? No, because when a particle and an antiparticle come together, they annihilate each other and produce energy. If this view were true, then nothing would produce unlimited amounts of energy by repeating the process ad infinitum. That's not what happens. That's not even the view that's really put forth. Instead, rather, an already existing energy field is the starting point from which the particle and the antiparticle can come out and then go back into the energy field. Otherwise, we would have a violation of the previously mentioned first law of thermodynamics, that mass energy is constant. Did the universe always exist? No. Because if it did, we wouldn't be here. Everything would have already dissipated an infinite time ago, according to the second law of thermodynamics. So this leaves an evolutionist with an untenable choice. He can either choose an open universe or a closed universe. If the universe is really open, then it's open to entities outside of it coming in, as in possibly the creator. On the other hand, if it's closed, then there's no escape from the heat death that we're going to discuss in just a few slides from thermodynamics, that everything is continually dissipating. The question that goes along with the second question, did the universe always exist, is, did the universe cause itself to exist? And I've had a number of people who have answered the question that I just posed, did the universe always exist, in the affirmative? And when I showed that couldn't possibly be the case, and we get to this question, I say, did the universe cause itself to exist? And the answer in the affirmative to here, even though that contradicts the previous answer they gave. No, the universe couldn't have caused itself to exist any more than anything else can cause itself to exist. Have you ever seen that water bottle down there, or a chair, or anything? Have you seen anything cause itself to exist? Neither have I. Well, if not any one thing can cause itself to exist, why should we expect the entirety of the universe to cause itself to exist if it's really the sum of all of its parts? No, the universe did not cause itself to exist. Otherwise, it would have had to have existed before it existed to cause itself to exist. This is a logical contradiction. Or another way of saying it is, the universe would have had to have existed and not existed at the same time and in the same context. It's a logical contradiction either way. Now, I'd like to chain issues 1, 2, and 3 together to show a cosmological argument. The first is, by application, did the universe exist? Well, we're going to say yes. If it didn't, well, there's a local hospital down the road that we can send you to where they have little white coats. Did the universe always exist? Well, we just got done saying no, it couldn't have. And did the universe cause itself to exist? No. So therefore, the universe had no material cause. It could not, because all material possibilities are contained within issues 2 and 3. Therefore, there's only 2 possibilities, 2 alternatives. One is the universe had no cause, in which case you're an Eastern mystic, the conversation ends, and it's unscientific. That would be assigning an effect with no cause. Or the universe did have a cause, but that cause must be immaterial. Choose from the following possible list of immaterial causes: fairies, leprechauns, gnomes, my favorite with the skeptics, flying spaghetti monster, God, you name it. Oh, by the way, only God even has any testimony. So when somebody tells me that my theory is no better than a flying spaghetti monster, I will turn to that individual and say, I don't believe in flying spaghetti monster. You do. And I never get an argument on that point. It's not the creationists who believe in the flying spaghetti monster. I can also rearrange the blocks, and I can form kind of a flow chart or a waterfall effect. Does the universe exist? No. You belong in an insane asylum? Or yes. Does the universe have a cause? No, that's unscientific. Yes. Is the cause material or immaterial? If I assume a material cause, then I'll show a contradiction. Issue 2, namely, did the universe always exist? No. I'm sorry, it's no, because otherwise it would violate the second law of thermodynamics. Then issue 3, did the universe cause itself to exist? If so, that violates logic. We saw that earlier. No, the cause must be immaterial, and we're back to the set of immaterial choices that we saw earlier. It's rather powerful stuff, because what we have in effect is a mutually disjoint decomposition of all the possible cases. There aren't any others left to choose from. It's not as if you can say, I don't know, we'll wait until science comes along with an answer. Well, I'll just sit there and wait for you to come up with an answer then. In the meantime, this is the entire set of choices. You have to reckon it as one of these. Which one will you side with? How can the universe avoid heat death? Well, according to the foregoing, it can't, because it is a consequence of the second law of thermodynamics. If, in fact, the universe is constantly increasing in disorder, technical term entropy, then it will eventually, by Le Chatelier's principle, reach a state of complete dissipation. there won't be any motivation for anything left to occur. There will be no useful energy left, in other words. The universe will then forever after that point be completely deteriorated. Now, there are alternative theories out there, have been for some time. You could categorize them as either being constant or steady state universe. Either way, you got a problem. And that is, we said earlier, the new science better agree with the old science. And the old science still says the thermodynamics are there. They still have to be reckoned with, no matter what kinds of things have come along lately. How can any material travel faster than the speed of light? Well, maybe you didn't think it any could. In other words, we've never seen any such behavior. All known phenomenon that we've ever seen indicate that the speed of light is not broached. That is, it can't go faster than that. Maybe outside a tiny epsilon, and that's about as good as it gets. However, those who had involved themselves in the Big Bang will, for the sake of trying to account for the ambient temperature of outer space being 2.7 degrees constant throughout the entire universe now, have to posit things like a hyperinflation at 10 to the minus 31 seconds. Well, how do we know? How would we possibly know it's not, say, 10 to the minus 32 seconds, or 10 to the minus 31 seconds, or 10 to the minus 30 seconds? Nobody was there to observe any of this. We don't even have any instruments now that can measure anything that small, in time at least. And why only one? Why not more than one? Nobody's positing more than one. So if we only posit one, well, why should we believe that it occurred when there's nothing else that would have occurred before that? In other words, isn't the present the key to the past? Isn't that the mantra? Well, then we should see more than one of these, but we don't. Or nobody's even positing it. And for those of you who might be inclined to an old Earth position, such as Hugh Ross's group, I talked with them about this particular problem. They have no answer. I went over it in incredible detail with their staff. Unfortunately, not Ross himself. Not only do they not have any answers to this question, they don't have any to the next one. What is the origin, transportation, and distribution of carbon? I'd like some help from the audience at this point. What does this picture show as examples of carbon that you either can see or can't see? Anybody's hand up, please. Yes.
Coal and a diamond.
She named two, coal and a diamond. What else?
Grass is carbon.
Right, all that green material. Anything else? Back here again.
Carbon dioxide.
Carbon dioxide. Where did you get that from?
The picture.
That's right, somewhere in there. What else? It's something you can't see. Anything else? Still no takers?
Graphite.
Huh?
Graphite.
The graphites we already mentioned. Cool. Anything else? How about carbon monoxide? How about methane? How about any number of gaseous compounds that have carbon in them? My issue tonight is not with the carbon in those compounds or in those singular examples. My question is, where did the carbon come from in the first place? That's a problem that supposedly was solved in the late 1940s and 1950s. It was called the triple alpha process. Notice that under origin. And what does the triple alpha process amount to? Somewhere in red giant stars, at only one nuclear resonance, helium atoms, which each have atomic weight 4, come together to form a transitory species of atomic weight 8. And before it can fall apart in 10 to the minus 15 seconds, a third one comes along for our carbon 12. Oh, never mind. This book has something to say about the transitory nature of such species as being extremely unstable. Also at atomic weight 5. We have two separate barriers. So it's a highly unlikely process. It's not impossible, but it is highly unlikely. What happens to this carbon? Only in a supernova can this carbon be distributed throughout the universe. What becomes of it then? Does it jet all of its carbon out in one direction to the Earth to form miles deep, thousands of miles long coal beds in several places throughout the Earth? You can answer that one for yourself, perhaps. But you scientists out there, if you have a good mechanism that would get that carbon to here and get it to compactify into all those coal beds, besides all the other examples of coal that we have on the Earth, great, I'll listen to you. But you've got to come up with something that agrees with known scientific laws as we understand them today, not as is promised in the future. Where could we possibly get this stuff coming from in the first place? Minimum of 33 light years away from us. Now, some have suggested that there were actually stars in the known region of the solar system now. But I have to ask the same question. First of all, how do you know that there was such carbon existing in this area? How do you know that the stars were existing in this area? Red giant stars that would supernova. And also, even if they were to supernova, wouldn't that blast all the material out in every direction anyway? It still wouldn't, in other words, it's going against the whole notion of it compactifying. Compactifying means that it's coming together. But this would be blowing it apart. No, there's got to be a better explanation than this, but I'll leave it to you folks to try to come up with one. In other words, it's still unexplained. And one real problem I have is that nobody is even discussing that problem. I thought that they might have when they were giving the Nobel Prizes out, and maybe they did, but I didn't catch on to that one. All right, so let's go to the matter of how do any stars exist at all? I mean, otherwise you don't have your red giant stars for your supernova. Let's assume that you have all of the mass confined to an infinitesimal volume. That would be a volume that's arbitrarily small as small as you want, close to zero, but not exactly zero, and that somehow or another there's a Big Bang. Let's just assume that for the moment. Now, do you recall Newton's first law? The one that says objects that are in motion tend to stay in motion and objects that are at rest tend to stay at rest? What will happen to the particles that would come out of a supposed Big Bang? That would be the inflation of sorts. What will happen to those particles? They will keep going and going and going and never stop going away from each other. What do you need in order to have a star? You need to have them coming the other direction, compressing. We have a hard enough time trying to compress gases now. Hydrogen, helium, doesn't matter. You need a specific compression device. In fact, there shouldn't really be any stars at all. But here's the flip side of it. Even if you assume 20 billion years, a generous time scale for a long old earther, a big banger, there are approximately 10 to the 21st stars that are, I don't know how they count these things to that magnitude, but supposedly there's that many in the universe. That would imply that there are 50 billion stars average that were produced per year. And we get excited if we see one star coming out of one of those stellar nurseries that you saw on the first slide. Or you can say it's not even being produced at 50 billion every single year, in which case it's either going down or it's coming up. I don't care how you want to look at it, it is still an average of 50 billion stars a year. And if the present is the key to the past, then we should be expecting to see 50 billion stars per year, every single year, ad infinitum. Is anybody observing this? Have you heard the newspapers or the radio or the TV saying anything like this? I haven't either. But if you do, let me know. I'm all ears to hear that. I would love to see somebody make good on this claim. How do moons form? Let's even assume that we have stars and planets orbiting about them. Jupiter, Saturn, Uranus, Neptune. These are the gaseous planets in our solar system. What are their moons, though? Are their moons gaseous? No, they're solid. How do you get a solid moon from a gaseous planet? Do you blast the gas? Do you try to get at the core? You're probably not going to get anywhere trying to get to the core anyway because of the huge gravity involved. No, there's just really no good explanation. And by the way, so let's suppose you even assumed a stellar hypothesis. That is, that the bodies of the universe were forming out of these gases that were somehow compressing. Don't ask me how. Why then gaseous planets, but the nearby objects around them aren't gaseous too? Instead, they're solid. No. On the other hand, we have a moon around our Earth. Well, what are some of the hypotheses that have been put forth with respect to getting a moon around our own Earth? Maybe it was captured. That is so unlikely a hypothesis that not even the evolutionists believe that that's the case. But for those who do, I have another question. Why don't we see examples of other tries? That is, other bodies coming in and not performing like our current moon does. Maybe hitting the Earth, maybe flying by in somewhere, maybe they're, who knows what. I don't see any examples of other tries, but come forth with them, please, if you have any ideas. Another more popular hypothesis is that something impacted the Earth, caused material to jet out beyond Roche's limit, which is about 1 to 2% away from the Earth, and voila, a moon. Well, let's think about that. What would it take, first of all, for it to hit the Earth? Well, first of all, if you're going to say the Pacific Ocean region, there better not be an ocean there, because otherwise you'll be blasting an ocean out. Okay, fine. We don't have an ocean in the Pacific Ocean region. All right, let's suppose that it's even big enough. You might even have to have something that's moon-sized to begin with to have something blasted out of significant size. Well, as the material is coming out, if it hasn't reached Roche's limit, it will continue to fragment until it reaches that point. And more than likely, it won't even reach that altitude before it starts coming back down again, not coalescing, and there goes your moon experiment. But let's suppose that you even have enough material jetting out beyond Roche's limit. It not only has to aggregate, it has to compactify, because that's how we know our moon does exist now. It's in a compactified state. It's not a bunch of little tiny grains that are somehow loosely aggregated and sticking to each other. That's not what we know our moon to be. Oh, there's a few other problems too. Even if you get beyond this point, you have three possibilities. You either have that the material has exceeded escape velocity, in which case it will keep going and going and going and never stop going away from the Earth, only to be captured by the Earth on some chance event. Or it will fall back to the Earth because it hasn't even reached orbit velocity. Or if it reaches orbit velocity, it also has to have a tangential velocity imparted to it perpendicular to the velocity at which it was coming out of the Earth in the first place, with no known source of the tangential velocity. These are just some of the problems that you have in trying to create a moon. Okay, somebody produce the evidence. I'd like to see how in the world, if I could use the pun, how in the world we could get a moon to come out of our world, out of our Earth, or any other thing that is not just plausible, but actually occurred. Here's an interesting quote from Wikipedia. Since tidal forces overwhelm the gravity that might hold the satellite, whatever satellite it is, together within the Roche limit, no large satellite can gravitationally coalesce out of smaller particles within that limit. What is the ongoing source of comets? There are two kinds of comets, short-term and long-term. The short-term comets might be things like Halley's Comet that have a period of less than or equal to 200 years. And they could be perhaps explained by the Kuiper Belt or the interplanetary disk. The problem is with the long-term comets. Now, some of them might be explainable by the same means, but not necessarily all of them. For this, the Oort cloud was hypothesized, spelled O-O-R-T. What might you ask is an Oort cloud? It's like a dirty snowball, an automatic pitcher, throwing out things very conveniently, of course, to whenever there are comets that are going into the sun, losing their material or whatever, so that we still see an ample supply of comets running around. Nobody has ever seen an Oort cloud. Nobody has any actual evidence of an Oort cloud. It's just a hypothesis. It would have to be far beyond the solar system in any event if it ever were seen or observed. But I'm empirical enough that if somebody wants to produce for me the evidence of an actual Oort cloud, fine, we can talk about Oort clouds then, and what kinds of things come out of Oort clouds. Meantime, if there is no evidence, then I will lay it aside and say you can keep trying all you want, but all you have is a grandiose hypothesis and nothing further. But let the evidence come forth. How do any elements heavier than iron exist? In that same year I was referring to, I took a course in modern physics, and in chapter 9 of this book, I won't turn to it, is a chart called the average binding energy per nucleon curve. It maximizes out at atomic weight 55, 56, somewhere in that area. In other words, where you would expect iron to occur. Which is another way of saying that all other elements are not as favored to form as iron is favored to form. Maybe we could see, perhaps, hydrogen eventually, by accretions, getting to this point. Although I have those problems with carbon, you know. What do you do for all the elements beyond iron? Iron is atomic number 26. Cobalt, nickel, copper, zinc, all the way up to uranium. In other words, all those elements from 27 to 92. We're not counting the synthesized elements beyond that point, 93 to 116 or so. We're not counting those. Well, they're just not as favored. All right, what has been put forth as a hypothesis? Supernova. And what is a supernova going to do? It's going to explode everything out in all conceivable directions. However, are we going to get any of those elements to be in sufficient quantities to be mineable on the Earth, or anywhere else for that matter, if they're all being blown to bits throughout the entire universe? Let me know if you've got a good answer for that one too. How do peptide bonds exist? In my hands are representations of amino acids. A left-handed one here and a right-handed one here. I'll get to the subject of left-handed in the next slide. Next topic, that is. The representation has a carbon with an oxygen and a hydroxyl group. This is otherwise known as a carboxylic acid group. On the other side, a nitrogen with two hydrogens, that's an amine group. In the middle, a carbon atom with a hydrogen and a functional group, which may either be another hydrogen or any of 19 other functional groups. This is a representation of an amino acid. Peptide bonds are amino acids that link together. So if I were to put this in your perspective, NHCHCO, NHCHCO, that's the way a peptide bond forms a protein. In the process of forming a bond, the hydroxyl group of the carboxylic acid and one of these two hydrogens drops out to form a water molecule. Have you ever heard that explanation that life began in a warm little pond? Just how is that going to occur when a water molecule must drop out, not be absorbed by the amino acids? This is a problem. Okay, so there's no warm little pond. What else do we have to figure in? How about if we have an oxidizing atmosphere, like our ozone layer? Well, the oxygen, the free oxygen, is going to destroy the peptide bonds and may even go ahead and destroy the amino acids too. On the other hand, if you don't have an oxidizing atmosphere, you have a reducing atmosphere. No ozone layer, and instead the UV rays come in and destroy the amino acid. In other words, everything had to be in place. The ozone layer and everything else. By the way, amino acids do not form peptide bonds out in the open. They can't because of the problems that I've just mentioned. Instead, they're carefully sequestered inside bodies, away from the water that would otherwise cause them to go back to starting materials. If we don't have any of these peptide bonds, we don't have proteins, we don't have enzymes, we don't have life. And by the way, without biochemistry, it's amino world. Regarding the left-handed, there we go, you can see very clearly in this or on the slide that these two representations are mirror images of each other. You can draw a mirror between the two. Can you see that very clearly in the back, maybe? I hope so. If not, you can pull out your chemistry textbooks after this talk is over, or look them online while we're talking. But the one thing that you can't do is superimpose one on top of the other. Stick them on top of each other so that they match. It will not matter as long as you don't break the bonds. It's not possible to because of the spatial arrangement. This cube represents what happens when we superimpose a tetrahedron into the cube. I don't think it's any accident that 2 of the 5 perfect solids are in view here. One is, in fact, embedded in the other. I think that's an example of design, but you decide for yourselves. Whether you want to call these stereoisomers, enantiomers, chiral compounds, as long as it's 4 different constituents around this carbon atom, there's no such thing as superimposing a mirror image on top of itself, again, if all 4 of them are different from each other. What happens when you try to compose them in the laboratory from neutral ingredients, neutral energy source, neutral environment? What will you get? 50-50 mixture, plus or minus a small percentage maybe for measurement. Why, you might even be able to get things to go slightly in a different direction. Maybe a little soil clays here or there. You might get it to be 1% difference, maybe at most. Or you might have the Murchison meteorite come in, like it did on September 27, 1969 in Australia, which has an even bigger disparity. But it's still not 100-0. Every single amino acid in every protein of every species is only one of the 2, left-handed one. No right-handed ones. The right-handed ones exist in other places, like bacterial cell walls, to prevent enzymes, which are left-handed proteins, from destroying the bacteria. I'd also like to mention something about the bond angle. If I were to say take the red outsides and the gray inside, that's what I mean by the bond angle. Any of the others will do because they have the same measure. And we can use Euclidean geometry to calculate the bond angle. If all the constituents are equal, the answer is the arc cosine of -1/3, which is approximately 109 degrees, 28 minutes, 16 seconds. It's an exercise that can be done in high school. I didn't learn about it until I was a freshman in college, and apparently nobody else does either, but it's clearly available. If the entities are not equal, then we can have a means of detecting what it is that we have in our compounds by reason of measuring the actual bond angles and comparing them to the tetrahedral bond angle. The R group that is the functional group will either stretch or compress depending upon what it is, and we can identify, or at least have another indication of what kind of a functional group it is, and thus what kind of amino acid it is. There is no reason why we can't have an all right-handed chain as opposed to an all left-handed one. It's not favored to have mixtures of them, as this book by James F. COOH points out. He was a professor at Cal State Northridge, now deceased. But there's no reason why you can't have an all right-handed chain. Isaac Asimov tried to say something about this matter. He said, well, it just happened one way or the other. It just happened that they all went left-handed and it spread across the face of the globe this way. If he were here, I would have asked him, how do you know? What leads you to believe from the evidence of science that we actually have all left-handed amino acids in proteins everywhere. What is the scientific evidence to say that it must be this way when you start off with neutral ingredients, neutral energy source, neutral environment? I also read a 300-plus page book on the subject that claims to go from non-parity of particles all the way up to that point. Not convinced. Show me how it actually occurred, now how it was hypothesized to occur. I'd like to say something about an earlier topic that feeds into this. This is my organic chemistry textbook from when I was an undergrad. This is an admission by the authors Morrison and Boyd regarding the matter of stereoisomers, which, by the way, are necessary to produce any of these structures, including the ones we've just been referring to. Indeed, we deal with optically active substances to an extent that we may not realize. We eat optically active bread and optically active meat, live in houses, wear clothes, and read books made of optically active cellulose, the proteins that make up our muscles and other tissues, the glycogen in our liver and in our blood, the enzymes and hormones that enable us to grow and that regulate our bodily processes, all these are optically active. Naturally occurring compounds are optically active because the enzymes that bring about their formation, and often the raw materials from which they are made, are themselves optically active. As to the origin of the optically active enzymes, we can only speculate. The situation is no better than when this book was being written in 1972. And it was known more than 100 years before that. What turned non-life into life? Let's suppose that I start off with a dead dog. There was somebody who was coming to one of my talks earlier that objected later on to my using this illustration, but I still think it's viable. Suppose I give you a dead dog, freshly killed, within 3 or 4 days, whatever. Let's suppose that dead dog has all the constituent components. It has the heart, the liver, the lungs, the brain, the blood vessels, the spleen, the muscular structure, the nervous system. I give you the whole thing, carte blanche. One small task, Hercules, breathe life into that dead dog. What's the matter? Is this not a small task for Hercules to perform? Aren't you Hercules? Well, maybe the problem is bigger after all. And if you can't breathe life into an existing dead dog, what makes you think you can breathe life into a set of materials constructed into a dead dog? But even if I give you the dead dog, already there, breathe life into it. You've got a lot further to go, of course. You have only hydrogen to start with, or maybe just that infinitesimal before the Big Bang. Never mind all the problems that we saw earlier about the binding energy per nucleon curve of trying to construct the rest of the elements. Never mind all that. There is no spontaneous generation. That was disproven by Pasteur in the 1860s. And in various things ever since then by almost everybody else. There is no Goldschmidt hopeful monster. And no, we don't have scenarios about RNA doing all the work. That's still a theory. Life only comes from life. That's all we've ever known. That's all we've ever observed. But again, I'm an empiricist. You show me non-life coming into life, I'll listen, with some provisos. How does metamorphosis occur? There are typically 4 stages, you might recall from your biology, about metamorphizing insects. Egg, larva, pupa, and adult. I could even grant you the adult laying eggs. Those eggs hatching into larvae and the larva turning into pupae. Would somebody please tell me how that pupa, in its mushy state, without any control of its own destiny, turns into an adult? Okay, let's see some evidence. Let's see some examples of how that mechanism works. I mean, I'd like to know. I've been waiting for all these years, and I'm not being disdainful. I really want to know. Would please somebody tell me? Then I can take this slide off, and we'll only have 15 slides instead of 16. And as I said earlier, you can say, well, we don't know. We'll just sit there and wait until science comes up with an answer. Very well, I'm just going to sit there and wait. And wait. And wait until you've come up with an answer. And until you have come up with an answer, you have a hypothesis. That's all you have. Earlier, I referred to Evan Schutz's flaw in the theory of evolution. He has a poignant statement to make about all these kinds of hypotheses that people make without evidence to support them. Step after impossible step is begged in the course of these polemics. By the way, just in case you think I'm just throwing around textbooks without knowing what I'm talking about, here is a copy of the Phi Lambda Upsilon Register. I'm a member of this honorary fraternity in chemistry. I proudly wear that badge, despite being mostly a mathematician. How do major morphological changes occur? Here are some that I've listed in going from one to another, from major class to major class. If you go from a fish to an amphibian, how do you go from no metamorphosis to metamorphosis? How do you go from a two-chambered heart to a three-chambered heart? If you're going from amphibian to reptile, now you're going once again from metamorphosis back to no metamorphosis, and the fertilization is from external to internal. Okay, suppose you're going from reptile to bird. How do you get from cold-blooded to warm-blooded and from scales to feathers? And finally, if you're going from bird to mammal, how do you go from wings to paws, hands, or hooves, and feathers to hair? And you'd have to have these morphological changes and so many others besides. This is only, of course, scratching the bare surface. Be true of both male and female, essentially co-located to form a colony. I'm waiting. Last topic for this evening, what creates information from gibberish? Communication, if you have a class, requires a sender tuned to a receiver. The receiver is tuned to the sender, and there is a medium that promotes rather than interferes with communication. I would ask, where do the senders, the receivers, and the media come from? But I'll even give you them for the moment. If I have a sequence of numbers or letters scattered about, that's not likely, that's very likely to have come from chance. If they are ordered, that's not likely to come from chance. That's what we believe. We have a means of measuring such things. It's called the autocorrelation function. If I put up the numbers 1 through 10, we see that that's not much likely to have occurred by chance. We can form the autocorrelations and find this out. On the other hand, if it's mixed up, like 1, 8, 3, 2, 5, 7, 4, 6, 10, it's more likely to have occurred by chance. And again, the autocorrelation function can measure such things. And in the grand scheme of things, there's also the glorification of the autocorrelation function called the ambiguity function. Maybe somebody out there has worked with radar, in which case you would recognize the ambiguity function in connection with range and velocity. If you want to bury a code, you do work in things like this. We need to have information to construct any of the structures that we have. We also have a measure of information entropy as well as energy entropy that I referred to earlier. Instead of heating gases, we're scrambling words. But it's much the same sort of sum of W log W is what we use instead, with a minus sign in front. So if we need information, for example, between DNA and proteins, the DNA code for the proteins code for the DNA, well, how are you supposed to get one from the other when you've only got one at most in the first place? But even if you have both of them, how do you get them to communicate so that one is coding for the other and the other is coding for the one? This is another example of a chicken and egg problem that is so common in so many of these things. And by the way, as I mentioned in my first version of this talk, which came first, the chicken or its egg? God. But of the two, a hen and a rooster came first. It's not Adam and Steve rooster, and it's not even Guinevere hen. It's Adam and Eve chicken. In answer to these 16 issues, I'd like to pose 16 others. But they are 16 famous scientists. I could have pulled more of them if I'd wanted to. Maybe you recognize some of those names. Maybe you recognize all those names. If you even have an undergraduate degree or anything that's a fraction thereof, you'll recognize every single one of those names because they're in your modern physics, chemistry, mathematics textbooks. What else do they have in common? No, the lettering is green. What else do they have in common? They weren't evolutionists. There were a few who are not on this list that were, but not too many. You might recognize those names as being the founders of modern science. Without them, we would not have modern science. We'd still be, relatively speaking, in the Dark Ages or the Middle Ages or whatever kind of ages you want. We would not be anywhere near to what we were without these giants of science. I dare anybody to think that he could go back into the past with Alex Trebek and compete with any one of them in jeopardy in his field. We'll see who pays for the dinner. Here's the list of references that I have been using from during this talk. You'll notice, by the way, only 3 of the 11, the ones that are in green, are in the creation camp. All the others are secular books. In fact, in the case of Evan Shute, he cites only one creationist reference throughout the entire book. All the rest of them are evolutionists. There's nothing like having the testimony of your enemies, if you're a creationist, do all the work for you. Nothing quite like that. I think we're ready for Q&A, unless you had some other...
Let's take about a 5-minute break.
Okay,
And come back to Q&A.
great. Thank you.